Hi, welcome to this video on measuring photovoltaic efficiency. In this segment, we're going to define the solar standard and solar test condition. And we'll also learn how to calculate electrical power, and we'll determine and calculate the efficiency using a photovoltaic specification sheet. So let's begin by going back to the solar resource, or the sun. In a previous lesson, we discussed the sun as being the largest fusion reactor in the solar system, and emits all forms of electromagnetic radiation. So we know the sun is bright. But how do we begin to relate that sunlight in the sky to the efficiency of a photovoltaic module? Well, again, in a previous lesson, we looked at the maximum efficiencies of laboratory-grade photovoltaic cells. And we see efficiencies constantly going up and up and up. How is that efficiency calculated, and how can we use that to our advantage as we begin to select a photovoltaic module? Let's begin by looking at how bright the sun really is. If we look at the sun in the sky on a general bright sunny day around mid-latitude on Earth, it will be approximately 1,000 watts per square meter. Let's dissect that definition a little bit. For that brightness, we consider a cloudless sky without any humidity. We define an area on the ground that's at least 1 square meter by 1 meter by 1 meter, or 1 square meter. We measure the brightness within that 1 square meter, and it is 1,000 watts. Dividing the 1,000 watts by 1 square meter gives us this definition of 1,000 watts per square meter. It's an easy number to remember and use, and it's pretty close to the actual terrestrial brightness, so we define this value as the solar standard. We combine that brightness with a standard temperature of 25 degrees Celsius, which is around 77 degrees Fahrenheit, and another term called air mass, to give a definition that combines solar and climatic conditions. The chosen air mass value is 1.5. We will discuss the definition of air mass in a following lesson, but suffice to say these three pieces, the brightness, the temperature, and the air mass, are what are going into determining the efficiency of our photovoltaic modules. Now that we know how to measure the solar input, let's begin to look at how we measure the electrical output from a photovoltaic module. Photovoltaic cells produce electricity, and we have to be able to measure that in some way. There are two fundamental units that we measure for a photovoltaic module to begin to figure out how much power it's producing. One of those units is voltage, and the other unit is current. Voltage is thought of as that push of electricity, how hard the electrical motion is pushing from one side to the other side of the module. Current is thought more of like a flow rate, or how fast the electricity is moving through the wire. When we take the voltage, that push, and multiply it numerically by the current, the flow, measured in units of amperes, we get the power, which is measured in watts. So, watts are equal to voltage in volts times current in amps. If we want to measure the efficiency of a solar panel, we need to know what the power going out is and divide it by the power going in, which is all based on the same unit of area. That's the general definition of efficiency. For a photovoltaic, we could measure the voltage and the current and multiply them together to get the output power. Then divide that by the area of the module. We then divide by the power of sunlight per square meter to yield the efficiency. We could do that outside in real time, or we could use the listed efficiency on a manufacturer's specification sheet. So how do we know a module's efficiency without having to go out in the field and measure each one independently? Well, manufacturers provide specification sheets for every commercial solar panel they produce, and they'll typically include 5 common terms. Those terms are always measured under standard test conditions, again, which is 1,000 watts per square meter, 25 degree air temperature Celsius, and AM 1.5 sunlight. The 5 terms are the voltage at maximum power, which is the voltage being put out by the solar panel, the current at maximum power, which is the current that's being put out under maximum power, and the power, or maximum power, which is the power of the solar panel, which is actually a calculation of the voltage at maximum power multiplied by the current at maximum power. The other 2 key terms are the VOC, or open circuit voltage, which is the maximum voltage that the cell will ever put out, and the ISC, or short circuit current, which is the maximum current the cell will ever put out, or the module will ever put out. We'll look at these 2 terms more in another segment. Now, once we know the voltage and the current listed on the cell's specification sheet, we can also figure out the power. Remember again that these are all under standard test conditions. If we look at a specification sheet like the one shown here, all the terms are listed. VMP, IMP, VOC, ISC, and maximum power or Pmax. There's also typically the power per area and a few other guides that can help you along, mostly to tell you that you're at standard test conditions. Some specification sheets will even show you what happens under different lighting conditions. So as you see here, the current will go down as the brightness of the sunlight goes down. So if you have a cloudy day, a photovoltaic module will still work. It will just output less than its maximum power because the current has gone down. There's also a temperature dependency value because solar panel voltage decreases as the cell gets warmer. So the efficiency goes down slightly from standard test conditions. Now, this isn't a big deal for efficiency, but it can be really important as we begin to choose proper wiring. We'll discuss that in the next course. Other information that's usually included in the specification sheets are the module size, weight, the impact loading, the fusing, and a few other electrical guidelines. So now that we looked at the specification sheet, let's begin to calculate efficiency. I've taken some voltage and current values from a specification sheet, the voltage at maximum power, VMP, and the current at maximum power, IMP. If we want to calculate the maximum power, which is in the units of watts, it's going to be equal to the voltage times the current. So 30.1 volts multiplied by 7.7 amps is equal to 232 watts, rounding up to the nearest watt. That would be the output wattage of this individual panel, but that needs to be adjusted for standard test conditions. The VMP and IMP are based off of standard test condition light levels. However, the panel is not 1 square meter in size, so we'll have to adjust for the size of the actual photovoltaic panel. The dimensions of the panel are listed on the specification sheet as well in units of length and width, usually inches and millimeters. For this particular panel, the length is 1.47 meters by 1.1 meters wide. Multiplying these two together gives an overall module area of 1.62 square meters. So now we know the area of the solar panel. If we take the panel's maximum power of 232 watts and divide that by the area of the panel of 1.62 square meters, we get 143 watts per square meter. We can then compare that to our power from the sun, which is also in watts per square meter. Efficiency is always calculated as power out divided by power in. So we take 143 watts per square meter in electrical output and divide that by our standard test condition solar input, which is 1,000 watts per square meter. When we divide these two by each other, the units cancel out and we get a decimal value of 0.143. Converting that to a percentage gives us 14.3%. So this solar panel would have an efficiency rating of 14.3%. The efficiency and the maximum power would also usually be listed on the specification sheet, but they're important concepts to understand and be able to calculate, as well as considering other important things when selecting panels for system design. So, in summary, you should now be able to define the standard test condition and brightness of full sunlight. You should also be able to calculate electrical power using current and voltage measurements to get wattage. And you should be able to both determine and calculate photovoltaic efficiency using a photovoltaic module's specification sheet. In previous segments, we discussed the components inside a photovoltaic module, like the individual cells and the wiring. In the next segment, we'll be discussing the external architecture, the pieces that connect the photovoltaic module to the overall electrical system.